We will now explore the behavior of forced oscillations. We will begin with a forced undamped oscillator of the form x double prime plus omega 0 squared x equals a cosine omega t. So omega 0 or omega naught we think of as the natural frequency of the system that oscillates, and omega we think of as the driving frequency of some motor or some external force. To solve this non-homogeneous problem, we first need to solve the homogeneous problem. X double prime plus omega 0 squared x equals 0. We have solved this problem many times before, and we see that the homogeneous solution is going to be C1 cosine of omega naught t plus C2 sine of omega naught t. Now, we would like to consider the non-homogeneous problem where omega is not equal to omega naught. In that case, we need to make a guess for the particular solution. We see that the right-hand side is given by a cosine omega t. So our particular solution should be of the form a constant maybe b cosine of omega t plus c sine of omega t. And then we're going to substitute this particular solution back into the differential equation. Now I know from experience that because there is no x prime term in the equation, that c will end up being 0. So I'm just going to substitute this back into the differential equation. So here, the second derivative of our particular solution is going to be minus omega squared b cosine of omega t. Another way to write that actually is minus omega squared xp. As you can see, because I'm only looking at the particular solution and the second derivative of the particular solution, no sine terms occur, and that is why the constant in front of the sine term would have been 0. So I'm going to substitute this back into my differential equation. That tells me that xp double prime plus omega naught squared xp is equal to, well, x double prime is actually minus omega squared xp, and then that's going to be plus omega 0 squared xp, and that is going to equal a cosine of omega t. So in fact, we can say that omega naught squared minus omega squared times xp is going to equal a cosine of omega t. And so actually, we can, instead of solving for a, we can actually just solve for what xp is. Here, we can see that xp is equal to a over omega 0 squared minus omega squared cosine of omega t. And that is our particular solution. I encourage you to go back and check that this is the particular solution by substituting it back into the differential equation. Well, that tells us something about our general solution. Our general solution is going to be the homogeneous solution, which was C1 cosine omega 0 t plus C2 sine omega 0 t plus our particular solution, a over omega 0 squared minus omega squared cosine of omega t. Now, we're going to be particularly interested in the case where we start with an initial position of 0 and an initial velocity of 0. The idea here is let's figure out what is the response of this system when we're driving it simply by the external force A cosine omega t. So we're not going to look at the influence of the initial position or the initial velocity, but we're going to assume that this system, what drives it is the external force. In that case, you can solve for the constants C1 and C2. What you will get is a solution that looks like A over omega 0 squared minus omega squared times cosine omega t minus cosine of omega 0 t. So that actually tells us that what will happen is that C1 will equal minus A over omega 0 squared minus omega squared, and C2 will equal to 0. Okay, so that is our system, but or that is the solution to our second order differential equation. But the question is what does this solution look like? What is the behavior of this solution? I see that it's just a cosine of omega t minus a cosine of omega 0 t, but what does it look like? Well, I want to show you an example. So actually, I'm going to let A be 50, omega be 26, and omega 0 be 24. So essentially, I want to drive this system at a frequency that's close to the natural frequency of the system, but is not equal to the natural frequency of the system. In that case, we get that x of t is going to be 1/2 cosine 24t minus 1/2 cosine 26t. Now, there's a couple terms that we can define here. One is called the mean frequency, and it is just the average of omega 0 plus omega. In this case, we would get a mean frequency of 25. And then delta is called the half difference. So this is going to be omega 0 minus omega over 2. And then the half difference in this case would be 1. Well, if we make these two definitions of omega bar and delta, then we can use a trig identity to rewrite this solution as 2a over omega 0 squared minus omega squared times the sine of omega bar t times the sine of delta t. So in this case, I really encourage you to read through the textbook and see how you can convert this solution, a solution of this form, into a solution of this form, using a trig identity for this for sine omega bar t times sine delta t. Well, in this case, we get that 2a over omega 0 squared minus omega squared is actually equal to 1. So we're left with sine of omega bar t, so sine of 25t, times the sine of t. And so what you see is a fast oscillation multiplied by a slower oscillation. In fact, we can think of sine t as being like the amplitude of the faster oscillation. So the faster oscillation is occurring, but its amplitude is changing over time. And so what I've done is I've plotted this on the left, and you can see the slower oscillation, sine of t, which is this black line here. And then that actually creates an envelope for the faster oscillation. So underneath that, you see the faster oscillation, whose amplitude is changing over time. So we see this very quick oscillation that increases in amplitude and then decreases and then increases and decreases again over and over again. So the amplitude has its own periodic behavior. The phenomena that describes this is called beats. So what's happening is that the oscillation is occurring in beats, with one fast oscillation, which is governed by the amplitude, which is at a slower oscillation. I'd like to show you what a mass spring system would look like that's experiencing this behavior of beats. So what I'm going to do is I'm going to open up slopes, and I already have the system loaded in here, where A is 50, omega naught is 24, so you can see the constant C is 24 squared, or 576, and then this is driven at a frequency of 26. So the mass spring, if we go ahead and load this animation, it starts off with no amplitude, and the amplitude of that fast oscillation increases and then decreases, and then increases and decreases again, so that amplitude is experiencing a periodic behavior.